Welcome to a code report solution video. In this video, we're going to be solving one problem in 24 different programming languages, the 18 languages that you can use on LeetCode.com plus 6 others. So these are the 24 languages we're going to be going through. The 6 that are not able to be used on LeetCode.com are APL, BQN, Clojure, Haskell, and the D language. And stay tuned to the end of the video to see the comparison of benchmarking the performances of the different solutions, according to LeetCode at least. So the problem we're going to be solving is problem 1 from contest 327. If you're watching this when this video comes out, it will be the most recent LeetCode contest that happened, and the problem is entitled Maximum Count of Positive Integers and Negative Integers. The problem statement is as follows. Given an array nums sorted in non-decreasing order, return the maximum between the number of positive integers and the number of negative integers. And it says at the bottom, note that 0 is neither positive nor negative, and the constraints for this problem most importantly are that the length of our array is not going to be larger than 2000. It's less than or equal to 2000, meaning that the time complexity of our solution isn't really going to matter too much. So the 3 examples that LeetCode.com gives us are the following. The first one is -2, -1, -1, 1, 2, and 3. And basically what we want to do is we want to count the number of negative numbers, which are going to be in red, count the number of positive numbers, which are going to be in green, count those up. So you can see on the left here, the red numbers represent how many negatives we have, and the green ones represent how many positives. And between those two numbers, we want to take the maximum. So if we take the maximum of these two numbers, we're going to get 3, 3, and 4 for each of our 3 test cases. So pretty straightforward. Hopefully this makes sense to everyone. And there are a number of ways which we can solve this in our different programming languages. The first, of course, being binary search. We're only going to look at this solution in C++, and the other ones are going to involve reduction. So the first one is just using a single reduction. We can do this either using a for loop or by using an algorithm, a fold or reduce. And then the second, or I guess third way to solve this is using 2 reductions. So some languages have a single algorithm called count that you can pass at a predicate. Others you can use filter and then just take the length of a resulting list. And in Python, we have an equivalent thing to filter called list comprehensions, which we're going to use. So across all of our 24 languages, they are going to fall into these different categories. And you'll note that J, APL, and BQN are sort of off to the side. We are going to solve those at the very end, and we're going to go and look into detail of how you build up the BQN solution. And these kind of fit into category 3.1 or 3.3. And you'll see when we get to it why that is. So our first solution we're going to look at falls into category 2.1 using for loops. Actually, our first 3 all fall into this category, which are going to be C, Go, and PHP. And we're going to start with the C solution. So these are not my favorite solutions because I don't really like writing for loops, but you can see here we're looping through all of our integers in nums, and we are basically just going to check if it's greater than 0, increment our pos, which stands for positives, and if it's less than 0, increment our neg. And at the end, we're going to use a ternary expression. If positive is greater than negative, we return positive, otherwise return negative. Pretty straightforward. Moving on to the Go solution, very similar. The main difference being that we don't have a ternary operator in Go, which means you have to do something at the bottom where it's very similar to the ternary operator. You just need to use an if-else branch. Moving on to the PHP solution, note that there's no syntax highlighting because, believe it or not, I could not figure out how to get syntax highlighting working with VS Code. But this is very similar to what we just saw with our last 2 solutions. The main difference, once again, being the final statement. We used a ternary operator in the C solution. We used an if-else branch in the Go solution, and we're using a max function in the PHP solution. So pretty straightforward. If you like for loops, this is probably one of your favorite solutions between the C, Go, and PHP. Moving on to our first solution from category number 3 that uses 2 different reductions. This is going to be the Python solution. So here we're using 2 list comprehensions and the length function. This is basically going to count up the number of positive and negative numbers, and then we just pass the result of each of these 2 list comprehensions passed to length to max, and that's going to give us our answer. Moving on to our next 3 solutions, this fits into category 3.1, the languages that don't have a single algorithm, but we can compose filter and length or count. You can see they are named different things in different languages. So Dart is the language at the top. Their filter algorithm is called where. You pass this a predicate, which is either going to check whether it's greater than 0 or less than a 0, and then call length on that, pass those 2 to max, and you're good to go. Swift does the same thing, except they call their filter, and they call their length count. And Erlang, very similar. calls their filter, and their length. Moving on to two other solutions that follow the same pattern, JavaScript and Typescript. These solutions are identical if you look at the bodies. The only thing that's different is the function signatures, obviously because TypeScript has types. Pretty straightforward. They both call their filter algorithms filter and their length functions length. Moving on to our two Lisp solutions, Clojure and Racket. These actually fall into two different categories. 3.1 is for Clojure and 3.3 is for Racket, because Racket has a single algorithm that takes a predicate to count up the number of numbers that meet that predicate. So Clojure, you need to call filter and count, but Racket, you can just call count and pass it a predicate. Note that I really like this about Lisp languages is their predicates end in question marks, so you can tell without even looking at the function that these return booleans. That's what a predicate is, so very nice. Moving into our solutions that strictly fit into the 3.3 category that have a single algorithm to count up the number of elements that match a predicate are C#, Elixir, and Kotlin. All of these are very similar, minus the spelling. They call their algorithm count, and they each take a predicate. The spelling of the lambdas or the anonymous functions are slightly different in each language. And once we do this, we pass it to the maximum function, math.max in C#, max in Elixir, and max of in Kotlin. And that is our solution for these three. Moving on to our next two languages, Scala and Ruby. These are grouped together because they're the two languages that don't have a prefix max function. So in Scala, it is a member on our integers or our lists, I guess. And on Ruby, it's the same thing, but it's postfix. So you sort of build up a list. And other than that, they both have an algorithm that is a single algorithm. We don't need to call filter plus length. It's just count. So nice that across most of these languages that do have a single algorithm, it has the same name for it, count. Moving on to our next two solutions are Java and D. These two are grouped together because they require casting. You can see that Java has to cast, I believe it's a ulong, which is what the count function gives you to an integer, and I believe it's the exact same thing in D. Note that Java does not have a single algorithm. They make use of the streams API. You call filter and then count, and then for D, you can make a single call to the count algorithm. Moving on to our next solution is Haskell. This is the one that starts to add something that's different to everything we've seen before. So we have filter for filtering, we have length for calculating the length, but note that there's only one length here, and that's because we're making use of a function in the data.function module called on, which is also known as the sci-combinator. So what the sci-combinator does is it takes a binary function, which in this case is max, and a unary function, which in this case is length, and it applies the length, the unary function, to each of our two arguments, positive and negative here. And therefore, we only need to spell length once, whereas in all the other solutions that didn't have a single algorithm, they would have to call filter twice and length or count twice, which is slightly irritating in my opinion because it's redundant. So you making use of the sci-combinator, which is called on in Haskell, we can eliminate one of the calls to length. And we'll see in the array solutions, J, BQN, and APL, that we can do a lot more elimination of this redundancy. Moving on to our C++ and Rust solutions. For the C++ solution, we're actually going to do something fun. So I'm going to pause here and think of the algorithm that you can use to solve this problem. And specifically, the solution we're going to look at here is the one that's time complexity is logarithmic, big O of log n. So if you are thinking std binary search, you are incorrect. If you are thinking std upper bound or lower bound, you are also incorrect. The correct answer for this problem is equal range. And there's actually all four of these algorithms that you're looking at right now are all logarithmic in time complexity. The time complexity is big O of log n. There's a fifth one, partition point, which many people don't know about. But for this problem, what we want is equal range. And that's because equal range, given a range defined by two iterators and a value, is going to return back to you two iterators that match the first element that is equal to that iterator, equal to that value, and then the first value that's greater than that value. So it basically defines a range of all of the values in your sequence that are equal to the value that you're searching for. And with these two iterators, A and B, we can very quickly, therefore, calculate the number of elements that are less than that value, aka negative numbers when our value is 0, and the number of values that are greater than 0, aka our positive numbers. So we do that using std distance and nums begin A, std distance B, nums n. And then we pass those two values to std max, and we're good to go. So equal range is exactly the algorithm that we want. And I saw that one of the top solutions using C++ algorithms on LeetCode was 2 calls to lower bound, but that's not actually what we want here. The algorithm that we want is exactly equal range. So moving on to a couple other C++ solutions, if we want to do the 2 calls to a single algorithm, that would be 2 calls to std count if. Note that this is the pre-C++ 20 solution. If we have C++ 20, we can use the ranges versions of these, which omits us having to use the iterators. And one other C++ solution we're going to look at is a single algorithm, which is going to be the call to std accumulate. And in this case, it looks pretty messy because we have to initialize a std pair, and then we use structured bindings, but we can't do that inline in our Lambda. So it ends up looking pretty messy, but this basically goes through and creates a new pair for each of our iterations and adds one to our positive value in our pair, or adds one to our negative, depending on whether the value is positive or negative. And then once we have those 2 values, we just pass them to std max. So those are our 3 different C++ solutions. Getting close to the end here, we're moving on to our Rust solution. Our first Rust solution that we are going to look at uses 2 different calls to filter and count. So basically, this is our 3.1 solution for Rust. And here, note, because we have move by default, we have to clone our nums the first time we pass it to filter and count so that we don't destroy the value. And then on the second call, we can just directly call filter and count on it. And then we can pass these 2 pos and neg values to std compare max, which will do what we want. The second solution we're going to look at was my first attempt at basically doing a single reduction, the equivalent to our accumulate in C++. And this is the following. So we are using fold now, which once again, we are initializing a pair of values. In this case, we can just use the language tuples that come with Rust. And then we're using pattern matching. However, I did not really like this solution, so I tried to improve upon it, and I came up with the following. Basically, ignore pattern matching and just do the same thing that we were doing in C++, which is quite a bit nicer. And if we can reduce the number of lines in the solution by 1 if we factor out the binary operation that we're passing to our fold algorithm and just put that on the first line and call it op. And this is actually my favorite version of all of the 4 Rust solutions that we've seen so far. Last but not least, we move on to our 3 last languages, J, APL, and BQN, which all have these incredibly cryptic, if you don't read J, APL, or BQN solutions. But they're basically doing the same thing as our 3.1 solutions. And I'm going to build up very quickly right now the BQN solution. So let's hop over to BQN pad and take a look. All right, so here we are in BQN. Note that we are only showing the evaluation of the last expression in our REPL here, but in order to show previous expressions, the evaluation of them, we can just add this show command, and we get the evaluation of all 3 of our test cases that we saw earlier. So right now, we're just showing the input as the output, but let's start to build up our solution. So here, first thing we want to do is count the number of negatives. So if we check which of our values in x, our argument, are less than 0, we get a Boolean mask, and then we can sum these up using a plus reduction, and this will give us the number of negative numbers. So 3 for both of our first 2 test cases and 0 for our last one. Then we basically want to do the exact same thing, put this in parentheses, and concatenate that with the beginning, and turn this to a less than or a greater than sign. We also need an x in here. And this will basically give us the count of our negative numbers on the right and the count of our positive numbers on the left. And we can just replace this concatenation binary operation with the maximum, and then that'll give us our answer, 3, 3, and 4. So this effectively is our solution here, but it's not what I showed on the previous slide. So let's refactor this to what I had shown before. So let's comment this out, and we can then compare what we have now. So the first thing we should do is make this point free. So we have basically a unary operation here, a unary operation here, and a binary operation. So if you've watched my other videos, you'll know that this corresponds to a fork. And we can basically get rid of this by putting the identity function, do the same thing over here. And now we have it in point free notation. So there's no mention of our argument x here. The next thing we can do is borrow from what we had in our Haskell solution. So in Haskell, we only had 1 length. The equivalent of our length in BQN is this plus reduction, and we have 2 of them here. So we can reach for the psi combinator, what was called on in Haskell, and it's called over in BQN, and basically do the following. Get rid of the plus reduction in both expressions, and then add this to our max reduction in the middle with the psi combinator. And what this says is our two arguments on the left and right being passed to our binary operation, before we pass them to our binary operation max, pre-process them with this unary operation. So we're basically applying plus to both the return value from 0 less than x and 0 greater than x. The next thing we can do is try and factor out this 0. So note that the only thing different on the left and right unary operations that are being applied to our argument first is the binary operation. The 0 is the same and the identity is the same. So we can actually take the 0 outside, bind this as the left argument, and then delete, 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 and delete. And we're good to go. And this is so beautiful in my opinion, because in all of our previous solutions that fell into the 3.1 category that didn't have a single algorithm, we needed to make 2 calls to filter, 2 calls to length, pass in 0 2 times to our 2 of our different binary operations. So there's just so much redundancy. Whereas here, we've only got 1 0, 1 plus reduction, and there's no mention of filter because we're not really doing a filter here. We're doing a Boolean mask and then a sum reduction. But 1 mention of each of our binary operations. So like we don't have anything repeated that doesn't need to be. We don't have any repetition at all for that matter, because nothing needs to be repeated. We just need to say everything once and then compose things using our combinators. So we have our psi combinator here, our phi combinator here, and then partial application or binding with our 0 for the left argument of the unary function that results from this composition of our phi and psi combinator. Probably none of that makes sense. Stay tuned to my composition intuition talk, which is coming out in June of 2023 this year. Yes, absolutely beautiful. Hope you enjoyed this little diversion into BQN. Back to all of our solutions. So we did a deep dive into our BQN solution, but as you can see, the APL and J solutions are basically identical. They just have different spellings of the Unicode symbols or glyphs. My favorite is BQN, followed by APL, and then by J. So if we go back to the different categories of solutions that we mentioned at the beginning of this video, of all of these solutions, I would have to say that C++ is my favorite, the #1 solution, because of the stood equal range algorithm that we have access to. My second favorite is the Rust solution. They get the second place medal because compared to the solutions that are able to do this in a single loop or a single reduction, I thought Rust was the best. And third place goes to Kotlin because I think it has the cleanest way of spelling the 2 reduction version. And the most beautiful solution, as you could probably guess, in my opinion, is of course BQN. So if we juxtapose these next to each other, you can see C++ at the top with the equal range algorithm, Rust in second place with the single reduction, and Kotlin with the 2 reductions for third place. And most beautiful award goes to BQN. Last but not least is a comparison of the runtimes of all of the solutions that were runnable on LeetCode, which is 18 of them. And the runtimes, as reported by LeetCode, are the following. So in first place is Rust, followed by Java, which I have a hard time believing because Java is a garbage collected language, followed by C, then by Go. A little bit confusing that C++'s equal range solution is slower than Go's, Java, or C's, and Rust's. So I think that these performance runtime results should be taken with a grain of salt, if not completely ignored. Maybe it only works intra-language because it does make sense. If you look at just the 3 C++ solutions, the equal range is the fastest, accumulate, which is a single reduction, is the second fastest, and then 2 reductions is the slowest. So maybe within a language it makes sense, but as you start to compare them across languages, doesn't really make sense. But read into this what you will. Links in the description to all of the solutions by language. And the last thing that I'll say is if you enjoyed this video, consider checking out one of my 2 podcasts, Algorithms plus Data Structures equals Programs, or ArrayCast, where we talk about array languages. Thanks for watching. I hope you enjoyed. I hope you learned something, and have a great day.